So we're really starting to wrap our heads around ratios and proportions. In this lesson, we're going to focus more on proportions. But before we get there, I wanted to make sure we hammer out a few very common misconceptions or trouble points about ratios. So you all remember our sign for a ratio, which is identical to a division sign, one thing over another thing. And it means, for every number of something, there are this number of the other thing. So what are ratios used for? Units, you all know that. When units are ratios, there are three areas of frequent confusion that arise, and I want to go through these quickly before we go any further. The first is when the number 1 is not explicitly stated as part of the unit ratio. We're going to take a look at an example of this with speed in just a minute. The second area of confusion is when the label of the unit does not show that it's a ratio. For example, watt, which seems like it's describing a single entity, but it's actually describing a rate of joules per second. The last area of confusion is when the parts of the unit are not understood. So even if you know that a watt is a joule per second, if you don't understand what a joule is, then it's virtually impossible to grasp the full meaning of a watt. Alright, let's look at some quick examples. Let's look at our speed example. Our cheetah is running 25 meters per second. What does this mean? It means the cheetah runs 25 meters in every second. Or we write it as 25 meters per second. Here we explicitly show that the meters are over the seconds. But to make it even more clear what we're talking about, let's put a 1 here. Because the cheetah is running 25 meters in every 1 second. Now we know the 1 doesn't change the meaning of it, but it really explicitly shows here that the seconds are separate from the meters, and the 25 corresponds to the meters, and the 1 corresponds to the second. Let's look at another example. Here's a density of 7 grams per liter. That's 7 grams for every 1 liter. And you can start to imagine, say we had 2 liters, then it's easier to see we'd have 14 grams. How about if we'd have 350 newtons per meter squared of pressure? Well, 350 newtons for every square meter. Let's look at our second misconception. When the unit does not explicitly show that it's a ratio. A perfect example is watts. Now, you saw this earlier, and you might remember that inside a watt are actually 2 units, joule per second, a unit of energy per unit of time. Now let's look at a microwave that has a 1,000 watt rating. What does that mean? It doesn't mean that the microwave comes with 1,000 of anything. It means that it operates at 1,000 joules per second. So it dissipates or converts 1,000 joules of energy into microwaves and heat and light in a second. So back to what we were saying earlier, that's 1,000 joules for every second. So it's not a quantity that the microwave has, but rather a rate that describes how the microwave works. But because scientists have abbreviated it to one word, it's easy to forget that it's a rate and it contains a ratio. Let's look at one more example. Here is a Pascal, which is a measurement of pressure. Now remember, pressure is a ratio of force per area. And a Pascal actually contains the units of newtons per square meter. Say you want to know the air pressure at sea level. So you look it up and you see it says 101,325 pascals. Well, what does that mean? Well, we know that a pascal is a newton per meter squared. So the pressure is 101,325 newtons per square meter. And as we've been reiterating, that means 101,325 newtons for every 1 square meter. So on every square meter, there's an average of 101,325 newtons of force pushing down on it. And that gives us a lot of useful information, because say we have an area that's 25 square meters. Now we know that for every one of those square meters, there's 101,325 newtons pushing down on it. So we just have to multiply by 25, and we'll know the total force that's pushing down on that 25 meter square area. We were just using a proportion to solve that little pressure problem, and you'll use them again and again in science. So I think it's time to take a look at what they are. Here you see two ratios on opposite sides of an equal sign, and that's exactly what a proportion is. Two equal ratios make a proportion. Now let's go back to an equation that we saw in the introductory lesson. 2 over 3 equals x over 6. This was indeed a proportion, and we could solve it by noticing that 3 multiplied by 2 to get 6, so 2 multiplies by the same 2 to give us 4. So we agreed that 2 over 3 equals 4 over 6. But let's take a look at really why that is. We have 4 over 6, and we can break that into 2 times 2, which is 4, over 3 times 2, which is 6. And we know from multiplication properties that that's the same as saying 2 over 3 times 2 over 2. And we all know 2 over 2 is 1, so here we have 2 over 3 times 1. And of course, 1 doesn't change the fraction. So we've proven that 4 over 6 does indeed equal 2 over 3. So what does this demonstrate? Well, in a proportion, the numerals on each side of the equation are different, but the value of the fractions is the same. Put another way, the relationship between the numerator and the denominator is constant. That's why we always divide the numerator and the denominator by the same number when reducing fractions. That's keeping the relationship between the numerator and the denominator the same. So let's see if that helps us solve this one that I claimed was very tricky for people. 5 equals 6 over x. Well, the key here is actually identifying this equation as a proportion, because number 5 over here is indeed still a ratio. We call it a unit ratio because it's over 1, but it's still a ratio. So we have a proportion. 5 over 1 equals 6 over x. Now let's solve it the same way we did the others. 5 times something equals 6 on the top. Well, that would be 1.2. So we have to multiply the denominator by the same amount, and we get 1.2, therefore giving us x equals 1.2. So we just had to remember that we had a unit ratio there, and then we could solve our proportion like we're familiar with. Now here's one more way of looking at things. An equal sign is like an evenly balanced scale. It must keep equal amounts on both sides. So you could have 5 on one side and 2 plus 3 on the other side. But if you multiply one side by 4, say, then the balance tips. But if you multiply both sides by 4, then we're even again. So if the scales are equal sign, then a proportion is like an evenly balanced scale of ratios. Say we put 4 over 9 on this side. What could we put on the other side to keep the scale balanced? Well, we can't change the value of the fraction, so we'd have to only multiply it by something equal to 1. But we can change the numerator and the denominator as long as we keep the relationship the same. So let's multiply it by 1, or 3 over 3, to give us 12 over 27. And now we have our proportion. In these 3 lessons, we've covered the fundamentals of ratios and proportions. In the next lesson, we'll look at different kinds of proportions, and we'll focus on something called a constant of proportion, beginning with the number pi.